Hello. In the previous lecture, we completed proof of Galois theorem on showing that if f is solvable by radicals, then its Galois group is a solvable group, at least when the characteristic is 0. We also mentioned that this statement is actually if and only if, so the converse of this statement is also true. That means that if the group of automorphisms of a splitting field of this polynomial over the base field capital F is a solvable group, then the polynomial is solvable by radicals. So let me go through the statement. So if F is a characteristic 0 field and small f is a non-constant polynomial, if I denote a splitting field of this polynomial by k, splitting field of this polynomial f over the base field capital F by k, then this polynomial is solvable by radicals over the base field capital F precisely when the group of f automorphisms of the field K is solvable. In order to show the converse of this statement, meaning assuming that the group of automorphisms is a finite solvable group and deducing that the polynomial should be a solvable group, it should be solvable by radicals. We needed to understand finite solvable groups a bit better, and we showed that every finite solvable group has a chain of subgroups. Each one is normal in the previous one, and the factor groups are cyclic groups of prime order. So because the group of automorphisms, f automorphisms of the field K is a solvable group, if I call this guy G0, then it has a normal subgroup where G0 over G1 is a cyclic group of prime order, and that one contains another group that's a cyclic group of prime order, and so on till we get to the identity. So again, all of these factor groups, all these quotients are cyclic groups of prime order. Now, we can use the fundamental theorem of Galois theory and look at the corresponding chain of subfields. So we get a tower of intermediate subfields of K over F. The fixed points of G0 would be the base field F. Then we get the next intermediate subfield, the fixed points of G1 that we denote by F1, and then the fixed points of G2 that we denote by F2, and finally the fixed points of G sub n minus 1, which is the fixed point of the identity, and everything is fixed under the identity, so we get the splitting field capital K. So we get this chain of intermediate subfields, this tower of intermediate subfields, and we are going to denote this tower by Fi's. What we know from fundamental theorem of Galois theory is that because G sub I plus 1 is a normal subgroup of G sub I, the extension F sub I plus 1 over F sub I is a Galois extension. And moreover, if I look at the restriction function from the F sub I automorphisms of K to the field F sub I plus 1, it's onto, so we get the entire field of F sub I automorphisms of F sub I plus 1, and the kernel of this map is F sub I plus 1 linear isomorphisms of K. And that's exactly means the numerator here is precisely G sub I, and the denominator is G sub I plus 1. And we know that these groups are cyclic groups of prime order, so these groups are cyclic groups of prime order. So this means that we get this tower of field extensions, f sub i's, f sub 0, subset of f sub 1, and so on, such that each one of these field extensions are Galois, and the group of automorphisms, the Galois automorphisms, are in fact cyclic groups of prime order. Now, following Kummer, we know that we are in a better shape if we have enough roots of unity. So what do I mean by that? So Kummer told us that when I have, if my field extension is a splitting field of x to the n minus a, and if my base field has nth roots of unity, then this extension is generated by a single zero of x to the n minus a. It's a cyclic extension, and we completely understand the group of automorphisms by just looking at that as the nth root of A and see what the automorphism does to this element. And from there, we divide it by the nth root of A itself. We get a power of this nth root of unity. We showed that this is in fact an isomorphism. So what I want to just indicate here is the importance of existence of enough roots of unity in the base field. So because of that, we want to, so inspired by this Kummer extensions, we look at the degree of this field extension K over F. Let's suppose that M is the degree of this field extension, and we are going to add this mth root of unity to the base field F. So what does that mean? This means that we are going to look at a splitting field L of K, of the polynomial x to the n minus 1 over K. So we'll come back to this and see why it's going to help us a lot. But for now, let's say that this is, so L is a splitting field of x to the n minus 1 over the base field capital K. Because K over F is a normal extension and x to the m minus 1 has coefficients inside the base field, this splitting field is not only going to give us a normal extension of K, but it is also going to give us a normal extension of the base field capital F. And because I'm assuming that all these characteristics of these fields are 0, all the algebraic extensions are going to be separable, and therefore L over F is also a separable extension. It's normal and separable, and therefore it's a Galois extension. So L over F is a finite Galois extension. Okay, so and x to the m minus 1. So what are the zeros? The zeros of x to the m minus 1 form a subgroup of the field L, and it's a cyclic subgroup. Using results from group theory, you understand that this abelian group, in this abelian group, there are at most d elements with the property that a to the d is identity, and we showed that such a finite group is always cyclic. So we deduced that L has a cyclic subgroup of order M. And if I call that guy zeta, so we call that guy zeta, so it has multiplicative order M. And when I add this zeta to the base field K, I'm going to get L back. Notice that all the zeros of x to the m minus 1 are powers of zeta. And therefore, this L would be precisely the base field K joined with zeta. Okay, now we are going to add this zeta to all the Fi's that we have up here. So we are going to add it to F sub 0, add it to F sub 1, add it to F sub 2. So this way, all these fields are going to have enough roots of unity with the exception of the F at the beginning of the tower. So altogether, we end up getting this tower of intermediate subfields. F is contained inside E0, E in this one inside E1, and we continue like that. And we notice that we have this type of tower shape. So if I look at each one of the blocks of this tower, in each one of the blocks, I have F sub I plus 1 joined with zeta. That's my E sub I plus 1 over F sub I joined with zeta. That's my E sub I. So essentially, I've started with the cyclic extension of F sub I plus 1 over F sub I. I call it cyclic in the sense that it's Galois, and the group of Galois automorphisms of this extension is a cyclic group of prime order. Now I started with this cyclic extension. I added zeta to the both fields, and now I'm getting this extension up over here. And my claim is that the extension up there is still a cyclic Galois extension. So let's see why this is the case. So the first, in order to have a connection between this guy over here and the guy in the bottom, which is the field that's contained in all of these 4 fields, we are going to observe that F sub I plus 1 plus zeta, added zeta, can be viewed as a splitting field of the polynomial x to the m minus 1 over F sub I plus 1. I'm adding zeta to F sub I plus 1. So this is a splitting field of x to the m minus 1. But by a similar argument as we had up over there, I mean up here, over here, we can repeat that argument and say x to the m minus 1 belongs to this base field. F sub I plus 1 over F sub I is a normal extension, is a Galois extension. And now I'm looking at the splitting field of some polynomial in the base. Therefore, the splitting field would be a normal extension of, the base. So that, again, let's repeat this. So whenever I give you a tower of fields, so I give you a tower E over F, I give you a polynomial over the base. I tell you that this extension is normal. And then I look at a splitting field of F over E. Then the extension of L over F is a normal extension. This we have discussed and in previous lectures. You've seen this in your homework assignment as well. So because x to the m minus 1 belongs to the base of this tower, and F sub I plus 1 joint zeta is a splitting field of x to the m minus 1 over this field, we deduce that F sub I plus 1 joint zeta is a normal extension over F sub I, characteristic 0, therefore it's a Galois extension. So again, f sub I plus 1 over f sub I is a normal extension. X to the n minus 1 belongs to the ring of binomials with coefficients over in the base field. And that implies that the splitting field of this binomial is still a normal extension over the base field. And therefore it's a Galois extension because characteristic is 0. Now I can use the restriction map. Because these are normal extensions, the restriction map would be a surjective map, and we get a surjective map from the automorphisms. So this is a diagram that we have. Let me rewrite it over here. So I have E sub I plus 1 going over E sub I, and this is a lift of F sub I plus 1 over F sub I, and now we know that this extension E sub I plus 1 over F sub I is Galois, F sub I plus 1 over F sub I is Galois, E sub I over F sub I is also Galois. So all the extensions are Galois because we already know that these guys are going to be Galois as well. So all the extensions are Galois. Now, either you can use the fundamental theorem of Galois theory, or we have proved this earlier, that by using the restriction map, we can deduce that the group of automorphisms of E sub I plus 1 over F sub I, when I restrict those to F sub I plus 1, is an onto group homomorphism, and the kernel of this map is precisely the automorphisms of E sub I plus 1 that are F sub I plus 1 linear, which means this is the kernel. Now, what is the lesson? Remember that this group of automorphisms is cyclic of prime order. Okay, so that's one thing we have to remember. What am I interested in? I'm interested in the top extension. I want to understand what is the group structure of E sub I plus 1, E sub I linear automorphisms of E sub I plus 1. Now we understood sort of that the E sub I plus 1 linear, E sub I automorphisms of E sub I plus 1 that are F sub I linear map onto a certain mapped onto this cyclic group. And the kernel is this guy. Now, let's try to understand what happens if I restrict this onto surjective map to this cyclic group, if I restrict that guy to the group that I'm interested in, meaning automorphisms of E sub I plus 1 that are E sub I linear. So this is precisely automorphisms of E sub I plus 1 that are E sub I linear. So an E sub I linear automorphism of E sub I plus 1, if I intersect it with the kernel of the map that we have, the kernel is this guy. So F sub I plus 1 automorphisms of E sub I plus 1. This means what? If something belongs to the intersection, what does this mean? If something belongs to the intersection, let's call this guy, let's suppose the theta belongs to the intersection. It means that when I restrict theta, so maybe I have to write it over here. So when I restrict theta to F sub I plus 1, it is identity. And when I restrict theta to F sub I zeta, it is still identity. So it sends zeta to itself, and its restriction to F sub I plus 1 is identity. So both of them together imply that when I restrict it to F sub I plus 1 joint zeta, it is still identity. But that's the entire E sub I plus 1. That means theta is identity. So altogether, we deduce that the intersection of the kernel of the restriction and the group that I'm interested in is trivial. So this means restriction induces an injective map from the group that I'm interested in, which means F sub I, E sub I linear automorphisms of E sub I plus 1. We get an injective map from this to the cyclic group of F sub I linear automorphisms of F sub I plus 1. So it seems too complicated. It's not like that. So let's, we have seen a more general setting in our discussions as well. So the general format is something like this, that if I start with a base field F, I give you an extension, let's be consistent with that, maybe F prime, and then I give you an extension of this guy, let's call it E. Let's put E and F prime together. This is exactly what we did with E sub I plus 1. Suppose all these fields are subfields of a larger field, and I look at the smallest field that contains E and F prime, and that's denoted by EF prime. Then the top argument, suppose that everything is Galois, then the top argument implies that E automorphisms of EF prime can be embedded into F automorphisms of F prime. And the embedding is coming from restriction map. So the restriction map is well defined, and it has no kernel, because if something is in the kernel, that means that restriction of this automorphism to F prime is identity. Already restriction of this automorphism to E is identity. So the restriction of this automorphism to EF prime is identity. So it was identity. So this gives us an injective map from E automorphisms of EF prime to F automorphisms of F prime. So you see, this is a quite general result. As long as we have that all the extensions are Galois, we can apply these restrictions and get the desired result. So altogether, what do I end up getting? I mean, what can I conclude? I conclude that I'm getting this chain, this tower of field extensions starting from F. So I get the next extension, we call it E0, then the next one we call E1, and we continued like that. And at the end, we reached to K joined with zeta. And what we showed so far is that these extensions, each one is Galois in the next one, and the E sub I automorphisms of E sub I plus 1 is cyclic. And moreover, this can be embedded into the automorphisms of F sub I plus 1 automorphisms of F sub I plus 1 that are F sub I linear. And because this was a Galois extension, we have that the cardinality of, okay, so this can be embedded into the automorphisms of F sub I plus 1 that are F sub I linear, and therefore by Lagrange's theorem, this cardinality divides the other one. Because the extension of F sub I plus 1 over F sub I is Galois, we get that this cardinality is precisely the degree of this field extension. And the degree of this field extension, because it's one of the blocks in this tower, divides the degree of the full tower, K over F. But the degree of K over F is M. So we deduce that the cardinality of the group of E sub I linear automorphisms of E sub I plus 1 divides M. So altogether, we are getting this tower. F contains inside E sub 0, E sub 0 contained inside E sub 1, and so on until we get K joined with zeta. Every block in this tower is a cyclic extension, and the cardinality of this cyclic extension, so each one of these extensions, okay, so F, no, but E naught contains zeta such that order of zeta is M, and this, okay, here it is N, and it is cyclic, and the cardinality divides it is cyclic and cardinality divides M. So altogether we created this chain of this tower of field extensions starting from the base field F, ending with a field that contains a splitting field of the polynomial F over capital F, except the first one, which is a generalized cyclotomic extension. So E naught itself, okay, maybe I can even update this and write down E naught is F bracket zeta, where zeta has multiplicative order M. It's the same M that all these degree extensions divide. It's the same M as all of this. So we get this kind of a picture, assuming that the group of automorphisms of K over F, the extension K over F, is a solvable group. We can add mth root of unity, where m is the degree of this extension, to the splitting field, and get a chain, a tower of intermediate subfields, starting from F, ending with K bracket zeta, such that each one of these blocks, except possibly the first one, is a cyclic extension, and the cardinality of this cyclic extension divides M, and all these fields except F contain an element of multiplicative order M. So we have already discussed cyclotomic extensions. We'll come back to those as well later. But for now, we look at the other blocks of this tower. Every other block in this tower look like this. So we have E over F, which is Galois. The group of automorphisms is cyclic. And the cardinality of this group, if the cardinality is N, then the base field does contain an element whose multiplicative order is N, and characteristic is 0. So every block, except the first one, which is a generalized cyclotomic extension, every other block looks like such an extension. E over F, cyclic Galois extension, cardinality, if the cardinality is N, the base field contains a multiplicative order N element. Now, in order to understand this kind of field extension, we are going to show a result to Hilbert, and it is called Hilbert's Theorem 90. Okay, so what is this statement? In order to formulate Hilbert's theorem 90, I need to define a Galois norm of an element in a finite Galois extension. So suppose E over F is a finite Galois extension. Then for every alpha inside the larger field, the norm of the Galois norm, the norm of alpha, is the product of all theta of alphas. Theta of alphas are called Galois conjugates, but here they might come with multiplicities, and we might have many of them to be the same thing. I'm not multiplying elements inside the orbit, but I'm looking at, I'm applying an automorphism, an F automorphism of E to alpha and multiplying all of them. So here I'm getting precisely the degree of this field extension many terms. Some of these terms might come with multiplicity. For instance, if alpha is already inside the base field, so from here, let me write it over here. So if alpha is already inside the base field, then norm of alpha with respect to this field extension is going to be what? Every single theta does not move alpha. So I get theta of alpha, which is alpha. I get alpha, 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 alpha. And how many alphas? Precisely the number of elements inside the group, the Galois group of this extension. But because it's a Galois extension, the Galois group, the cardinality of the Galois group is precisely the degree of this field extension. So we get that it is alpha raised to the power of the degree of the field extension. So for every element inside the base field, the Galois norm of the element is alpha raised to power the degree of the field extension. Okay, this is an example, useful example to have in mind. Let's start with a basic property of a norm. A basic property of norm is that for every alpha inside the larger field, norm of alpha belongs to the smaller field. Second property, when I start with non-negative numbers inside the larger field, I get non-negative number inside the smaller field, and this map is indeed a group homomorphism. It preserves multiplication. So norm is a function that preserves multiplication. You can compare this norm with the thing that we have already used many times when we started with a complex number and we send this to norm, complex norm squared. So that complex norm squared is z times complex conjugate of z. And the complex conjugate is precisely the other R linear automorphism of the complex numbers C. So R linear automorphisms of C consists of two functions, identity and complex conjugation. So the norm of Z with respect to the extension C over R is precisely the complex norm squared. Okay, so now we see a connection between complex norm squared as well. Let's go to the proof of this lemma. Let's see why we have that this belongs to the base field. We have seen that a good technique of showing an element belongs to the base field of a Galois extension is showing that it is in fact fixed under every element of the Galois group of this extension. So in order to show that the norm of alpha belongs to the base field capital F, it is enough to show that the norm of alpha is fixed under theta prime for every theta prime in the F automorphisms of the field E. So let's suppose let's pick the theta prime from F automorphisms of E, and let's apply this to the norm of alpha. Norm of alpha is the product of theta alphas as theta ranges over the elements of F automorphisms of E. Theta prime, being an automorphism, preserves multiplication. So this would be product of theta prime of theta of alphas as theta ranges in F automorphisms of the field E. Theta prime belongs to this group. Theta ranges inside this group. So as I multiply all the elements of a group by another element of the group, by Cayley's theorem essentially, or you can just follow from the definition of properties of groups, we can deduce that theta prime theta also ranges in the elements of this group. So as I multiply elements of a group by another element of the group, I just permute the elements of the group. So theta prime theta gives me again all the elements of F automorphisms of E. So I can essentially call them again, or you can call them theta double prime. That's a dummy variable anyway. So let's say it's the same as theta ranging inside the group, and I'm applying theta to alpha. And that's exactly the definition of norm. So I'm getting back norm of alpha. So altogether, we are showing that when I apply theta prime to norm of alpha, I get back norm of alpha. It's a fixed point of all the automorphisms, so it should belong to the fixed points, but it's a Galois extension. So the set of fixed points of F automorphisms of E is the base field capital F. So norm does belong to the base field capital F. So that shows the first part of the claim. Next part, I want to show that the norm is indeed a multiplicative group homomorphism. So I look at alpha 1 times alpha 2. I apply my norm function. But what is norm? Norm is product of theta of alpha 1 alpha 2s as theta ranges in the group of F linear automorphisms of the field E. But theta is being an automorphism, theta of alpha 1 alpha 2 is the same as theta alpha 1 times theta alpha 2. Now I can split the product and write it as product of theta alpha 1s as theta ranges inside this group, and product of theta alpha 2s as theta ranges in the F linear automorphisms of E. This part means I'm getting norm of alpha 1, and this part means I'm getting norm of alpha 2, and that's exactly the definition of being a group homomorphism. So norm does preserve multiplication, and that's true for every alpha 1 and alpha 2 inside E cross. So we get that it's a group homomorphism from E cross to F cross. Okay, so what Hilbert's theorem 90 give us is Hilbert's 90 theorem describes kernel of norm function when the field extension is a Galois extension, is a cyclic Galois extension. So if E over F is a cyclic Galois extension, it's a finite Galois extension, and the group of automorphisms is a cyclic group, let's say it's generated by sigma, then Hilbert's theorem 90 says alpha belongs to the kernel of this norm homomorphism if and only if alpha is of the form sigma of beta. Sigma is this generator of the group of F automorphisms of E. Sigma of beta over beta for some beta inside E. So norm of an element is 1 if and only if it is of the form sigma of beta over beta for some beta. Okay, so this is an if and only if statement. One side is much easier than the other side. Let's start with the easy direction. If alpha is of the form sigma of beta over beta, it is relatively easy to see that it is inside the kernel. Let's see why this is the case. In order to show this, let's understand, I want to understand norm. I want to understand norm of alpha, and norm is defined in terms of the F automorphisms of E. What do I know about F automorphisms of E? The assumption is that the F automorphisms of E is generated by the automorphism sigma, and it's a finite cyclic group. So suppose that it has n elements. Suppose that the extension is n, it's Galois, so the group of F linear automorphisms of E has n elements, and it's generated by sigma, so it should be identity sigma squared till I get sigma to power n minus 1. So that is the group of F linear automorphisms of E. Now, norm of alpha is what? Norm of alpha, if alpha is of the form sigma of beta over beta, is norm of sigma of beta over beta. But norm we have proved to be a group homomorphism, so it is norm of sigma of beta over norm of beta. So, and I want to show that this is equal to 1, which means I need to show that norm of sigma of beta is the same as norm of beta. This is what I need to show. Let's do it. What is norm of sigma of beta? Norm of an element means I have to apply elements of my F automorphisms of the field. I need to apply them to that element and then multiply them. So I apply identity to this sigma of beta. I get sigma of beta. I apply sigma to sigma of beta. I apply sigma squared to sigma of beta. I go on till I reach to sigma to power n minus 1, and I apply it to sigma of beta. And then I need to multiply them. So sigma of beta, we don't touch it. And then the next one is sigma squared beta. The next one is sigma to power 3 beta. The one before the last one is sigma raised to power n minus 1 beta. And the last one is sigma to power n beta. But sigma to power n is identity because sigma generates a cyclic group of order n. So sigma to power n is identity. That means sigma to power n beta is just beta. So as you can see, I'm just rotating the terms of this group applied to beta. The product doesn't change. After all, these are elements of a field, and a field is commutative, so I can reorder the terms. I can put beta at the beginning, and that gives me norm of beta. So altogether, we show that norm of sigma of beta is the same as norm of beta. This part of the argument is quite general. So norm of alpha is the same as norm of sigma of alpha, no matter what Galois extension I pick. Because when I apply sigma to all the elements of F linear automorphisms of E, I get back all the F linear automorphisms of E. So norm of alpha and norm of any other Galois conjugate of alpha are the same. Okay, so in particular now we get that norm of sigma of beta over beta, which is alpha, is norm of the numerator over the norm of the denominator, but they are the same, so we get that this has norm 1. As we saw, as we can see here, this direction is rather easy. So every element of the form sigma of beta over beta is automatically in the kernel of the norm function. The other side, however, it's a bit more subtle, and we need to prove the so-called Dirichlet's independence of characters. So what is this statement? At the surface, the statement has nothing to do with field theory. It seems to be a statement about groups. So let's see what it is. I give you a group G, I give you a field E, and I give you n distinct group homomorphisms from the group G to multiplicative group of E. And let's call them chi1, chi2, ... chi(n). So these are distinct group homomorphisms from G to E cross. Okay, so the claim is, what Dirichlet proved, is that these chi sub i's are E-linearly independent. But what does that mean, E-linearly independent? Somehow, I mean, the right setting is that you should think about them as functions from G to E. And in the set of all the functions from G to E, if you think about all the functions from G to E, then this is in fact a vector space. The set of all the functions from G to E is a vector space. And in that vector space, these chi sub i's are E-linearly independent. But we can say what E-linearly independent means without going to that vector space. So let's spell it out. When we say chi sub i's are E-linearly independent, we mean that if I give you an E linear combination of chi sub i's, which happens to give us the constant zero function, which means no matter what G I give you inside the group, this E linear combination ends up being zero. If this is the case, the E linear combination that I'm giving you should be the trivial one, meaning all the coefficients should be zero. This is the claim. The claim is that chi sub i's, these group homomorphisms from G to E cross, such a group homomorphism we also call a character of G, E character of G. But I prefer to refrain from that statement and call them group homomorphisms, but traditionally they are also called E characters of G. So chi sub i's are these distinct group homomorphisms from G to E cross, and claim is that then they are E-linearly independent, which means if some E-linear combination of them give us the constant zero function, then all the coefficients are zero. Okay, so that's the claim. This is Dirichlet's theorem, and we want to prove it. And the method of the proof is fairly similar to to the way that we showed that Galois extensions, okay, that fixed points E over fix of G is a Galois extension. And we showed that the cardinal and the degree of the field extension is precisely the cardinality of the group G. So we had a lemma over there, and the proof of the lemma was, so the way that we proved that result was like this, that we started with a subspace of E to the n, and we applied the group to that subspace, and the statement was that if the subspace is the G invariant and it is non-zero, then it has a non-zero fixed point. Here we are not going to use that result, but rather the idea inside the result. The key technique of proving that result was looking at smallest vector, non-zero vector inside that set, and trying to manipulate it and end up getting the fixed point. That was the idea. Here we are going to use this smallest linear combination that gives us zero as well, and manipulate it to get the desired result. Okay, let's see how the proof goes. We are going to assume to the contrary that I do have a linear, non-trivial linear combination that is zero. So that's the contrary assumption. So to the contrary assumption, I'm going to assume that there are vectors E sub 1 dot E sub n inside E to the n such that this linear combination is zero as a function. Again, this being zero means that when I plug in G, I always get zero no matter what G I plug. So as a function from the group capital G to E, I'm going to get the zero function.
So that's the definition of V. And the first thing that we notice is that this V is a non-zero set. Because of the contrary assumption, we get some non-zero vector inside this. The next thing that we notice is that it is in fact a vector space. It's rather easy because if I give you EIs and EI primes, and if both of them give us this zero linear combination, I can scale one of them and add it to the other one and use the distribution property and deduce that their linear combination is still inside this set V. So this V is a subspace of E to the n, and it's a non-zero subspace of E to the n. Now, let's do this manipulation that I've mentioned earlier. What is the manipulation here? If E1 En is inside V, what does that mean? This means that no matter what element of the group I plug in into the linear combination of E sub I, chi sub I, I'm going to get 0. So the element that I'm going to plug in is going to be product of two elements. One of them fixed, the other one ranging. So G0 times G is going to be an element of the group. I'm going to plug it in into this function that's constantly 0. I end up getting 0. Now I use the fact that chi sub i's are group homomorphism. So instead of writing chi sub I of G0 times G, I end up getting chi sub I of G0 times chi sub I of G. And this linear combination is supposed to be 0. Now, all of a sudden, I get a new linear combination of chi sub i's. This time, I am multiplying chi sub I by this constant. This is still inside E, and I'm multiplying chi sub I by this constant, and I'm adding them up. No matter what G I plug in, I end up getting 0. So this means that these E sub I, chi sub I, G naughts give me a new vector inside the vector space V. So E sub 1 chi sub 1 G naught, E sub 2 chi sub 2 G naught, E sub n chi sub n G naught. This vector also belongs to the vector space V. I'm kind of giving you a new action of the group G on this vector space V. The new action, when I want to apply the element G naught on the vector E1 En, it multiplies the first component by chi 1 of G naught, the second component by chi 2 of G naught, and so on. Okay, so I'm giving you this new action. And we notice that the number of non-zero components doesn't change as I apply G naught to the vector E1 En. Similar to the previous argument that we've seen, this kind of length of a vector can be helpful. What do I mean by that? So L of a vector, we define it to be the number of non-zero components of this vector. So length or support, size of the support of this vector. So the number of non-zero components of this vector. And this number is not changing as I apply G naught to it, because these chi sub I G naughts, all of them are units, are non-zero components, non-zero values inside E. So if E sub I was non-zero, then E sub I times chi sub I G naught is still non-zero, and vice versa. So this L of E doesn't change as I apply G naught to it. Have this in mind. Similar to the previous setting that we had, we are going to look at the smallest vector inside this vector space. So we are going to look at the minimum L of V among non-zero vectors inside this subspace, and let's assume that V naught is giving us such minimum. So V naught belongs to this subspace, and L of V naught is M. So it has the minimum number of non-zero components. By rearranging chi sub i's, reordering the terms that are non-zero, I can assume that the non-zero components of V naught concentrate at the beginning. So I get E sub 1 dot 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 E sub m that are non-zero, and then the rest of the components are 0. Okay, so now I'm in a good shape. I have to go back and use the assumption that chi sub i's are distinct. Because chi sub 1 is different from chi sub 2, okay, but first things first, I have to say that this m cannot be 0 because V naught belongs to this capital V means that E1 times chi 1 plus E2 times chi 2 dot 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 is 0. If m is 0, that means chi sub 1 of G should be 0. That's not possible because chi sub IGs, they are inside E cross. They are non-zero elements. Okay, so m is not 1. That means that I have at least chi 1 and chi 2 involved in this linear combination. Now I'm going to use the fact that they are distinct. Because chi sub 1 is not chi sub 2, they are different at least at some value, at some element of the group G. Suppose that chi sub 1 of G naught is not the same as chi sub 2 of G naught. Let's apply this G naught to the vector V naught. What do I mean by that? I mean this. Because this vector V naught belongs to the V, when I multiply the first component by chi 1 G naught, the next component by chi 2 G naught, and so on, I will be still inside this vector space V. So I get that E1 chi 1 G naught, E2 chi 2 G naught, and so on is still inside V. I want to manipulate this and make it make more 0 inside this vector. The way to do it is to getting rid of the first component. So this means I start with this being inside V. I want to get rid of this guy. So I need to multiply this vector by chi 1 of G naught and then subtract this one. I will be still inside V because V is a subspace, but then I get more zeros. But that's not possible, and that's how we reach to a contradiction. Okay, let's see. So this vector is inside V. I multiply E sub i's by chi 1 of G naught, and then I look at the difference. Because V is E linear, and this guy belongs to E, these vectors are inside V, this difference is still inside V. Now, when I compute, the 0 components are on the same spots, so they are still 0. The first component, I chose this scalar over here in a way that I get rid of the first component. So the first component is also 0. So now I get more zeros inside my vector, which is inside V. This means that length of W, L of W, is strictly less than M. I added one more 0 to this. But that's not possible if W is not 0, because among the non-zero ones, the smallest length was M. Now I'm getting something smaller. So the only possibility is that W should be 0. In particular, the second component should be 0. What is the second component? Second component is E sub 2, which is a non-zero number, times the difference between chi sub 2 of G naught and chi sub 1 of G naught. But this is also a non-zero component because we chose G naught this way. Because chi sub i's were distinct, I was able to choose G naught so that chi 1 of G naught is different from chi 2 of G naught. So this component is non-zero, therefore W is not 0. That's a contradiction. I found a non-zero vector inside V that has length less than the minimum. So I reached a contradiction. This finishes proof of Dirichlet's independence of characters. But what's the connection between Dirichlet's independence of character and Hilbert's theorem 90? So let's go back to Hilbert's theorem 90. In Hilbert's theorem 90, the assumption is that the norm of some element is 1, and we want to find a beta so that alpha is sigma of beta over beta. Let's manipulate our goal a bit. So we are looking for some beta so that alpha inverse times sigma of beta is beta. So it seems that it's not only about alpha, it's also about sigma of beta. So if I call this transformation that sends an element of E to alpha inverse times sigma of E, if I call that guy T sub alpha, so this would be a transformation from E to E, and if you, this is multiplication by number, alpha inverse, and sigma is F linear. So T sub alpha is an F linear map from E to E. And what we are asking for is whether or not this F linear map has a fixed point, a non-zero fixed point. This is what we are asking. So we're asking, does T sub alpha, which is an F linear map, have a non-zero fixed point? This is what we are asking. It's F linear. An alternative way of formulating it is asking, as an F linear function, does it have eigenvalue 1? Remember, if you have eigenvalue lambda, this means that there exists a vector such that T of V is lambda V. Now I'm asking, do we have a vector beta such that T sub alpha of beta is beta? So it's the same as asking whether or not T sub alpha has eigenvalue 1. Later, we will discuss minimal polynomials of linear functions, and we show that minimal polynomials, I mean, every eigenvalue is a 0 of a minimal polynomial of an F linear function. So that's a kind of hidden logic behind what we are going to do next. So what we are going to do next is to find minimal polynomial of T sub alpha. In particular, in order to understand minimal polynomials, we need to understand powers of T sub alpha, and minimal polynomial means, can I find a relation, algebraic relations between powers of T sub alpha? So this is the hidden logic between for our next step, where we are going to focus on understanding powers of T sub alpha. Okay, so let's go to the next step. We want to understand powers of T sub alpha. So I look at T sub alpha squared, apply to E. What does it do? T sub alpha, I have to apply twice. When I do it once, I'm going to multiply it by alpha inverse, apply sigma. When I do it again, I multiply alpha inverse, apply sigma to whatever I had earlier. But sigma is an F linear automorphism of E. So this means sigma of alpha inverse is sigma of alpha inverse, and then I get sigma squared of E. So altogether we get, now this time I need to multiply alpha inverse times sigma of alpha inverse, and then apply sigma squared to E. So it seems that each time I'm going to multiply by some element inside E, and then apply larger power of sigma. So let's check this by computing T sub alpha to power 3. T sub alpha raised to power 3 applied to E means I need to apply T sub alpha to what we had earlier. What we had earlier is over here. I put it over here. Now T sub alpha means I need to multiply alpha inverse by sigma applied to whatever we had. Sigma is an automorphism of the field. So this means I need to apply sigma to the first term, to the second term, and to the third term. And sigma of alpha is, sigma of alpha inverse is sigma of alpha inverse. I can take the inverse out. So I get that, so this alpha inverse is coming over here. sigma of alpha inverse is sigma of alpha inverse. Then I have sigma sigma, which is sigma squared of alpha inverse. And finally, I get sigma of sigma squared, which is sigma to power 3. So you see there is this pattern. I have alpha inverse, sigma of alpha inverse, sigma squared of alpha inverse, and then sigma to power 3 of E. This is for power 3 of T sub alpha. I can use this inductively and show that when I apply T sub alpha I times, then it's the same as multiplying alpha inverse, sigma of alpha inverse. I go, you see, 3, 2. I go till I reach to I minus 1. And finally, 3, 3, I, sigma to power I of E. So I get this element of E, I have to multiply by sigma raised to power I applied to E. In particular, when I plug in n, what do I get? T sub alpha raised to power n of E is, okay, so I take these inverses out. I get alpha times sigma of alpha times sigma squared of alpha times sigma to power n minus 1 of alpha, the whole thing raised to power negative 1, and sigma raised to power n E. But remember that this is a cyclic group generated by sigma, and where were we? Actually over here, sorry. Okay. It's a cyclic group generated by sigma, so this is the entire group of automorphisms. And then the norm of beta, or norm of an element, would be beta times sigma of beta times sigma squared of beta, sigma to power n minus 1 of beta. So here I have alpha, sigma of alpha, sigma to power n minus 1 of alpha. This is precisely norm of alpha raised to power negative 1. And sigma to the n is identity. So it's just E. And norm of alpha is supposed to be 1. So I get E. This means T sub alpha raised to power n is identity. So next, in fact, in the argument, we will see that we will show that this is a minimal polynomial of T sub alpha. So x to the n minus 1 is a polynomial that is satisfied by T sub alpha, and later it is hidden in the proof that we are showing that it is the smallest degree polynomial that T sub alpha satisfies. Okay, but let's use another angle of explaining the next step. By the angle of the minimal polynomial, I motivated you to think about powers of T sub alpha, and we reached to this equality. That's one way of finishing the proof. So this, by showing that this is the minimal polynomial and then arguing that 1 is a 0 of the polynomial x to the n minus 1. From there, you can deduce that 1 is an eigenvalue of this polynomial, and that finishes the proof. But we haven't studied that part of linear algebra over arbitrary fields, so we are going to use another technique. Let's go back to this angle of finding a non-zero fixed point, or finding these fixed points for T sub alpha. A common technique of finding fixed points for a group action is by looking at the center of mass of an orbit. So I give you an orbit, you look at the quote-unquote center of mass of the orbit, and that should be a fixed point of your group action. This is a common technique that's used in different parts of mathematics. Now we want to use that intuition. Okay, so the center of mass doesn't quite make sense in an arbitrary field, but we can use our intuition from the Euclidean space. I apply my group to an element of E, and I get this vector E T sub alpha of E, T sub alpha squared of E, and so on. and I look at the center of mass, and center of mass means I'm looking at the average of these elements inside E. Our intuition says that this should be a fixed point of my group action that's coming from the cyclic group T sub alpha. You see, T sub alpha raised to power n is identity. I can think about it as a cyclic group of order n. Okay, so that then our intuition says that this should be a fixed point. Let's simplify it a bit. Because it's a linear action, this constant should not matter. So this means I can just focus on this summation. So this means this summation should be an should be a fixed point of T sub alpha. Now, as soon as I find that for some E, this fixed point is non-zero, will be done. So our goal would now, and then our next goal would be to show first, this is indeed a fixed point, and second, I can find some E that this guy is not zero. So this is our next, these are our next steps. Let's start by arguing why this is a fixed point of T sub alpha. I apply T sub alpha to this summation. I use the fact that T sub alpha is linear. This means I can apply T sub alpha to the first one, then to the next one, then to the next one, and to the last one. And you see, each time the power of T sub alpha goes a bit up, one step up, T sub alpha of E and so on. And the last one, I get T sub alpha of to power n of E. But T sub alpha raised to power n is identity. That's what we showed. So we get back the first term that I was missing. I get back the summation that we started with. So it is indeed a fixed point of T sub alpha. Okay, so far so good. Now our next goal is to show for some E, this quantity is not zero. So I need to go back and study T sub alpha to power I. Remember, T sub alpha to power I is alpha times sigma of alpha. This number, this element of E raised to power -1, it's again an element of E times sigma to power I applied to E. So this summation, this linear this summation of E and T sub alpha applied to E and so on, this summation is the following linear combination of powers of sigma. Identity applied to E. Then T sub alpha is E1 sigma of alpha. T sub alpha squared is E sub 2 times sigma squared. Then E sub 3 sigma to power 3. And finally, E sub n minus 1 sigma to power n minus 1. So this summation turns out that the summation is only an E linear combination of these distinct group homomorphisms from E cross to E cross. You see, the powers of sigma are automorphisms of E. In particular, they are group homomorphisms from the multiplicative group of E to multiplicative group of E. And these are distinct group homomorphisms because these are distinct automorphisms and all of them send 0 to 0. So when I restricted them to the group of, to the multiplicative group of E, I still get distinct maps. So these are distinct group homomorphisms to E cross. Therefore, by the Dirichlet's independence of characters, they are E linearly independent. So by the Dirichlet's independence of characters, these powers of sigmas are E linearly independent. This means that this linear combination cannot be always 0. I can definitely find some E for which this linear combination is not 0. So I take that and call it beta. So for some E, this linear combination is not 0. I call it beta. Now I'm done. I found a fixed point of T sub alpha, which is not 0. That means that alpha inverse times sigma of beta is beta. That means alpha is sigma of beta over beta. That finishes the proof of Hilbert's theorem 90. Okay, so far so good. But what is the connection between this and Galois solvability theorem. The connection comes from the blocks of the tower. Remember, we wanted to study a field extension of a field of characteristic 0, which is a Galois extension, and the extension is cyclic, and it has order n. We have enough roots of unity inside the base field. From that, I want to deduce that E is indeed a radical extension, not any radical extension. It is precisely a Kummer extension. It's F joined with a solution of x to the n minus a for some a inside the base field. So that's my next goal. As soon as we show this, it's rather easy to finish the proof of Galois solvability theorem. Okay, so how can I do it? The magic comes from this nth root of unity. Remember, norm of an element inside the base field is that element raised to power the degree of the field extension. So norm of zeta is zeta times zeta times zeta is zeta to power n, the degree of the field extension. But zeta is also an nth root of unity. So zeta to the n is 1. So norm of zeta is 1. Now I can apply Hilbert's theorem 90. So zeta can be written as sigma of beta over beta for some beta inside E. Okay. Now what can I say about the Galois conjugates of beta? So sigma of beta is zeta beta. I apply it again. Sigma squared of beta is sigma of zeta beta. But remember, sigma is F linear. Zeta belongs to F. So it is zeta times sigma of beta. Sigma of beta is zeta times beta. So each time that I apply sigma to beta, I'm multiplying it again by zeta. So I can use this logic and inductively show that sigma raised to power I of beta is zeta to power I times beta. In particular, the orbit of F linear automorphisms of E, the F linear automorphisms of E, the orbit of beta under this group action consists of n distinct elements that they are beta, zeta, beta, and so on. These are distinct because zeta to power i's are distinct and beta is non-zero. So I get these n distinct elements inside the orbit. Remember, this orbit is enough to understand the minimal polynomial of beta over the base field capital F. Because E over F is a Galois extension, the minimal polynomial of beta over F is the product of x minus beta primes as beta prime ranges inside this orbit. So this product gives me the minimal polynomial of beta over F. So I need to understand this product. Remember, we had this kind of decomposition earlier when we studied Kummer extensions, and this were related to x to the n minus some element inside the base field. And so that element inside the base field should be the constant term of this. This means I need to multiply these constant terms to understand the constant term of the minimal polynomial. So product of these is precisely the norm of beta. So let's see what it is. It is beta times zeta beta and so on. Remember, sigma to power I beta is zeta to power I times beta. So there are n betas. So I get beta to power n. And 0 zeta, 1 zeta, 2 zeta, n minus 1 zeta. So I get an arithmetic progression for the powers of zeta. Starting from 0, ending with n minus 1. So when I add the powers of zeta, I get n times n minus 1 divided by 2. So I get zeta raised to power n times n minus 1/2. But what kind of element is this guy? If I didn't have this divided by 2 thing, then I was in luck because I know zeta to power n is 1. Okay, so I do have this denominator. What can I do? How can I get rid of it? I can square it. So if I look at the square of this guy, then there is no denominator over here. I get zeta raised to power n times some other integer. Zeta to power n is 1. So this means that this element raised to power 2, square of this element is 1. But in a field, in a field of characteristic 0, such an equation has precisely two solutions. So it's either 1 or -1. So this number, this element of E is either +1 or -1. So altogether we get from this equation, this element is either +1 or -1. So beta to power n is plus minus norm of beta. Remember, norm is always an element of the base field. So beta to power n is an element of the base field because it's +-1, plus minus of this element inside the base field. So let's call beta to the n to be A. Then zeta to power I times beta. Also, when I raise this guy to power n, I still get beta to the n because zeta to power n is 1. So those guys are also A. So I'm getting n distinct zeros for the polynomial x to the n minus b. So all of these are zeros of x to the n minus b, minus a, sorry. So again, I can use the generalized factor theorem, compare the degrees, compare the leading coefficients, and deduce that x to the n minus a is x minus beta times x minus zeta beta, and so on. But this is exactly the polynomial that we had over here, which was the minimal polynomial of beta over f. So altogether, we deduce that the minimal polynomial of beta over f is x to the n minus a for some a inside the base field. And therefore, the degree of the field extension, I mean, when I add beta is precisely n, and the degree of E over F was also n, so it is the same. So E is F joined with beta. Beta is a 0 of this one, so I can write it like the nth root of A, and the claim follows. Having this, we can easily complete proof of Galois solvability theorem. So assuming that I have this solvable group, we showed existence of a tower of field extensions that we denoted by E sub i's, where E sub i's are Galois extensions. Each one is Galois in the next one, and the group of automorphisms is a cyclic group, and it divides n, where n and E sub i's contain nth roots of unity. So I'm repeating here, I'm repeating the proof that I started with over here, and I've summarized it over this box, and I'm repeating this part at the end of the argument to make sure that we know what we were doing. I'm coming back to this page. So we constructed this chain of intermediate subfields. Each one was cyclic. The cardinality divides M, and we had an mth root of unity inside the base field, E naught. So that's exactly what I'm doing over here. I'm reconstructing these E sub i's. Now, because of the result that we proved, we know each one of these intermediate subfields, with the exception of the first one, is of the form, is a Kummer extension, is of the form E sub I joined with some n sub I roots of E sub I, some element inside the previous field. And the first one is just a cyclotomic extension, generalized cyclotomic extension. So altogether, we are getting that E sub m plus 1 over m over f is a radical extension, because each time I'm adding a solution to the x to the n minus a for some a and some n. So it's a radical extension, and this contains the splitting field of the polynomial f. Altogether, that means the polynomial f is solvable by radicals over the base field capital F. This completes the proof for now.